could you take your seats, please? It's about time we got started. We have essentially our annual, I suppose in a way, celebration, but also culmination of the Southampton students' academic year here. They come here for 8 months, arriving at the end of August, and then straight into research, essentially, with their advisors. And then they have to write a thesis, which they've all been doing over the last couple of weeks, which got submitted on Friday, I think. Maybe a couple of drips and drabs over the weekend. So that's all finished. And the last thing is the presentation, which they give here in front of all you chaps to show you what they've been doing. And also as a demonstration, I think, that of the quality of research that top master's level students, and or at least undergraduate, it's an undergraduate degree in a way, what that sort of level can achieve in research here in a fairly short period of time. It was really actually a short period of time. So while they've been here, of course, they've experienced some American culture, which they don't get in the UK. They've had an absolutely typical American election season to go through. That was very entertaining. It's absolutely typical, just like all other elections. There was a change in Prime Minister over the last summer, and now there's a frenetic election campaign that they'll go back to when they get back a chance to vote for that. Too late for Brexit, though, I think, unfortunately. And then the previous year, they had the excitement of Leicester winning the Premier League. Well, they missed that. But of course, it's back to Chelsea having won this year, so that's pretty boring. None of you are Chelsea fans, right? No. Good. Let's move on then to our first talk. So if any of you saw the notice about Claire Baker, so she actually had to leave because she had events with the UK national ultimate frisbee team over the weekend. So she had to go back early for that, and that's why she didn't make the talks here. So all of these students are essentially they're sort of multi-dimensional, as top caliber people usually are, sportsmen and musicians. We move on to Florence. Florence Kentucky Mary, who hails from Surrey, near London. She's a keen rugby player and plays for the University Southampton rugby team, women's team. She worked on Supernovae a little bit as an undergraduate, and while she's been here, she's been working with Akosh on I'll give you the talk in a second. And she's going to be moving on to do a PhD in IR laboratory spectroscopy after this at Imperial College in London. Without further ado, the title of her talk is the average characteristics of gaseous X-ray coronae around spiral galaxies, advised by Akosh Fogdat.
Hello. Can people hear me? Cool. Hi, everyone. As Jeremy said, I've been working with Akosh for the last 9 months, trying to study the average characteristics of X-ray coronae around spiral galaxies. So as we know, galaxies form within dark matter halos. That text says hydrodynamical cosmological simulation illustris, which models galaxy formation. As we know, galaxies form within dark matter halos, and as the surrounding gas falls on these dark matter halos, it's heated. But because this gas is at a very low density, its cooling time is comparable to Hubble time. So we should still be able to detect these X-ray coronae today. This is actually an image from illustris. Here we can see the galaxy, which is this tiny little dot right in the middle, and this is the hot extended X-ray corona. So it's notable that it's very far out from the optical galaxy itself. As we know, illustris overestimates AGN feedback, but we will compare our results to that in a bit. This is predicted around both elliptical and spiral galaxies, but around elliptical galaxies, we expect it to have evolved a bit more, as elliptical galaxies are supposedly the product of mergers and have a much more vigorous star formation rate history. They are also found within groups and clusters, so they themselves will have their own halo, which will interfere with the observation of the X-ray corona around individual galaxies. For this reason, we would like to study spiral galaxies. So there have been previous studies of spiral galaxies, a few. The best ones have been done by Akosh, but note that they are very high mass spiral galaxies. This is actually an image of one of them. But they're very high mass and very rare, and They've been observed to 60 kiloparsec, but we'll see that I managed to get a value up to 120 kiloparsecs or so. But because these are very massive, they're not a good representation of the overall spiral galaxy population. For this reason, we need to to fully understand the corona, we need to get the average properties of all these galaxies. So we need to actually go deeper and we need to get a bigger sample, but this isn't actually possible right now with Chandra. These values will be used to constrain galaxy formation to assist in creating the constraints within galaxy formation simulations. The reason we will, from this, we're going to do a stacking analysis to try and get an increase in the signal-to-noise ratio, and which can be done because we have a great increase in exposure time and will allow us to probe fainter limits. This can also enable us to look at larger radii around galaxies, and as we will be using the average properties, we'll be removing the effects of outliers, ideally. So these were the 3 multi-wavelength surveys we used: AGIS, Cosmos, and Deep2. These are the mosaic of the raw Chandra observations, which I find quite pretty. The Cosmos one is my favorite because it looks very aligned. In total, these are 11 megaseconds and cover 12.5 square degrees. Oh, one more thing. Yeah, each of these, because they're multi-wavelength surveys, have been covered by SDSS as well. So our galaxy sample has been limited to the redshift range 0.3 to 0.05, and our mass range of the log stellar mass has been limited to 11.9 down to 10.1. The mass has been calculated using SDSS colors and the mass-luminosity ratio from the Bell 03 paper. As mentioned earlier, we want spiral galaxies, not elliptical galaxies, but because of the distance of these objects, we can't just view them all and categorize them by eye. So we've determined them by determined the morphology using the SDSS color index U-G. We resulted with almost 7,000 galaxies and over 10,000 Chandra observations, which amounts to a total of 190 megaseconds, which is about 6 years of continuous observation. So we need to take into account the contribution due to objects within the stellar mass profile, such as within the optical stellar light profile, but the stellar mass such as AGNs and low and high mass X-ray binaries. So we looked at the stellar mass profile. Here we can see that that 99% of the stellar mass profile lied within 28 kiloparsecs. For this reason, we will study the regions 30 to 60 and 60 to 120 kiloparsecs using local background regions. To ensure that we don't have contribution due to nearby galaxies or point sources, we will also remove these before carrying out a stacking analysis. So these are the main results of my project. We have luminosity against stellar mass. Here in the low mass bin, we find a detection. It's 1.6 and 2.3 sigma, so they're not incredibly significant, but nevertheless, we have a detection there. These are the first points we have at these low stellar masses. These haven't been necessarily found before. We haven't explored this part because there's no lower mass in the 60 to 120 kiloparsec range, because the virial radius of these galaxies are expected to only go up to about 80 to 90 kiloparsecs, so we would be observing background. The reason why we can go to such low luminosities with this one is because there are over 7,000 observations here. Note up here, for the high mass, we've managed to get a 60 to 120 kiloparsec value, which again is 2.5 sigma, so somewhat respectable. As mentioned before, we compared our results to Illustrious. We know Illustrious overestimates AGN feedback, therefore there's less gas present in these outer regions. At every mass bin, my results were significantly higher than those predicted by Illustrious. My results actually also concur with the ones that Akos came up with for the 2 massive spiral galaxies, which is a good sign. From this, we can also calculate the density and therefore the hot gas mass in each of these regions for the mass spins that we have. We use this to calculate the baryon mass fraction within the mass spins within the galaxies within each mass spin, and we can compare the mass fraction we have with that of the cosmic baryon mass fraction. We observed less than 7% for every mass spin, which means that there's definitely baryons missing. They may be in the form of cold gas or be white straight, just not in the galaxy, but they're not in the form of hot gas as far as my results can tell. Yeah, and here's my summary. I did a stacking analysis of 7,000 galaxies, almost 7,000 galaxies, with a total of 6 years of exposure time. They are relatively weak detections, but nevertheless, there's detections in low masses. And there were missing baryons at every mass scale, so I don't know what to make of that. I don't know where they are either. But that's it.
Okay, time for some questions. Let's put the lights. Yes.
Have you calculated how much Sunyaev-Zel'dovich effect you'll see from this gas?
Pardon?
How much Sunyaev-Zel'dovich effect would be seen from this gas?
I'm going to say no because I'm not sure what that is. Sorry.
Akos
Akos might know, yeah.
But probably not much.
But the instruments are getting down to the microkelvin level. So it's from order of microkelvin, it's quite possibly detectable now.
The thing is that, I don't know about the resolution of the commission guarantee. Right. Yeah, okay, but we can talk about this after. I've been thinking about this before. We can chat.
Okay. Questions? Any more questions? Yes.
There was a factor of 100 or more difference between illustrious predictions and your detections.
Yes.
So is that too much? I mean, when you say overestimates, it's like by factor few, maybe, but a factor of 100 seems like not merely overestimating, but just getting it totally wrong. Well, on average, look at that. I mean, I can't see the scale too well here. On the right, I was looking at, look at the decades going, marching up there. Yeah. Any idea why?
I don't know about the simulation itself, no. Sorry.
Any suggestions? Well, the AGN feedback is, you say, is wrong, right?
Mm.
Can that explain all of the difference, or you think maybe?
I'm going to go with yes, but that's because I have very limited knowledge of the simulation, so
Well, that wasn't your words.
no.
You're allowed to not. Okay. Any other questions? Yes, Jason.
In the highest end, how did you end up with the upper limit? So you didn't detect those soldiers? I would imagine it would be a low limit.
Yeah, that really puzzled me as well. Something which,
Non-detection implies upper
yeah,
limit.
yeah, this one is an upper limit non-detection.
You didn't detect anything?
No, we didn't detect anything here, but we did detect something here.
The same object at a larger radius.
Yes, and that might be because there's a temperature profile of the X-ray corona. So we're probing different parts. If it peaks for like I think it's 0.2 of the virial radius it peaks. The virial radius of this mass spin is much larger than the virial radius of these mass spins. So this might actually correspond to the same virial radius as this, for example. But I haven't done the exact numbers. Well, I have, but they're in my thesis and I don't remember them right now.
Any other questions? Okay, great. Well, that's a huge amount of data that Florence went through for that long stacking. Thanks very much,
Thank
Florence.
you.
Okay, so next up we have Chris DeZera. Chris at least in the CV, it says he's from Bournemouth. Is that right, Chris? Are you from Bournemouth, or was that just where you were living while you were?
Yeah, I'm from Bournemouth.
Yeah. You just support Bournemouth or Southampton or neither?
Neither.
Neither, okay.
Yeah.
So from Bournemouth, right next door to Southampton, he's just down the road, across the bay. So Chris is a keen sportsman, but he's also a musician and plays piano, guitar, and he says here a Swiss accordion. So you know, if the astrophysics or whatever doesn't work out, Chris, you've got something to fall back on. So as an undergraduate, he did some research on quasars, and then naturally, of course, from doing quasars, you go into asteroids. And so he worked with Martin Albus. Following his work here, he's going to the other Cambridge University for a PhD course in essentially machine learning, big data. So his talk today, his thesis is on the spectral classification of small thermal infrared detected near-Earth asteroids advised by Martin Albus.
Oh. Okay. So, today I'm going to talk to you about the work I've been doing for the last 8 months with Martin on near-Earth asteroids. So, of the millions of asteroids that exist, a small fraction intersect or come close to the Earth's orbit, and this is what we call near-Earth asteroids. So, why should we bother investigating these? Well, firstly, they have orbits very similar to that of the Earth. So that makes it very easy for planetary scientists to go over, send probes, and analyze their properties. This tells us a lot about the formation and evolution of the early solar system. Secondly, since many intersect the Earth's orbit, occasionally they hit the Earth, we call these potentially hazardous asteroids, or PHAs. And knowing their sizes and compositions allow us to strategize how to best deflect or break up the asteroids. And thirdly, asteroid mining is soon to become a reality. And near-Earth asteroids are rich in platinum group metals, which are worth about $50 million per ton. And also some are rich in water, which is similarly valuable in orbit. So asteroid mining is attracting the attention of private and government interest. Most recently in November, the Luxembourg government invested 25 million euros in, I think it's a planetary resources company, to get an initial probing mission up by 2020. So there are, however, limitations. We are discovering near-Earth asteroids at an ever-increasing rate and at fainter and fainter magnitudes. So on the right here, we have the mean discovery magnitude against discovery year. So at the moment, 2017, most of the near-Earth asteroids that we're discovering are at about magnitude of 20, 21, which is very faint and makes it very difficult to follow up these asteroids after discovery. We need near-infrared spectrographs to get composition information. However, this is from the ground. This is limited by a very bright atmospheric background. So we need to make these telescopes very large, which is quite expensive. In the thermal infrared, between 5 and 20 micron, we can get the black body area of these asteroids, and then we can infer this. Well, we can calculate the size and albedo information. However, from the ground, these are also limited by the atmosphere and the telescope itself. So we want to, well, we'll have to use space telescopes for this, which again is very expensive. So we're looking for a cheap and readily applied alternative, and we're going to check whether it's any good. So our alternative is using optical spectra. It's an old method used by Bust and Binzel 2002. We classify the spectra into 3 broad classes: S-type stony, X-type metallic, and C-type carbon-rich. And we do that by looking at the main spectral features. So the first spectral feature we look at is, well, the main spectral feature we look at is the slope. So for S-type, we have the steepest slope. We have an intermediate slope and featureless, relatively featureless spectra for X-type, and featureless and even flatter slope for C-type. Additionally, we can use the 0.75 micron turnover in S-type asteroids over here. We don't know the physical mechanism of the slopes. However, the 0.75 micron turnover is part of a deep 1 micron absorption feature due to the absorption of pyroxene and olivine in silicate material. There's also an additional absorption feature below 0.5 micron that we didn't observe in this study. We should extend that in the future. So for thermal infrared observations, we see this relation by Meinzer et al. It shows that the albedo for S-type and C-type asteroids have distinct ranges. X-type, however, are just distributed through the whole albedo range. We have very few observations below around 10 kilometers in diameter. So we want to go down by a factor of 10 in size. We can see that S-type and C-types increase in albedo at these lower sizes. We want to see whether this is a selection effect due to smaller asteroids being naturally more difficult to observe because they reflect less light, or whether it's indeed a physical change. So we're going to combine the optical spectra, the classifications of optical spectra, with near-infrared spectra, with near-infrared observations, to check whether this relation extends down. And then we can observe, we can predict albedo from composition, or conversely, predict composition from albedo. So that's how far we want to go. So near-Earth asteroid spectra is just reflected sunlight, and we call this the reflectance spectrum. So what we need to do is divide out the sun's component. We do this by observing solar analog stars each night at the same air mass as the near-Earth asteroid, and then divide the two spectra to get the final reflectance spectrum. So we first go through the typical data reduction of wavelength correcting using the absorption features there, air mass correcting, getting rid of emission features, cosmic ray emission features, or cosmic ray features, sorry, and then dividing, getting our final result. We then also additionally smoothed it to get rid of or reduce some of the noise. So we used solar analogs from a list, a standard list used by asteroid astronomers, and they did span a very large range, surprisingly, from B1V to K2, or B1 stars to K2 stars. Since the slope of the asteroids is a key feature to figuring out its composition, we wanted to figure out whether the type of star used affects the overall classification, because then they themselves don't have the same slope as G2 type stars. So we found each of the slopes for the types of stars that we used in our data reduction, and we found that, in fact, G-type stars are all very similar to G2 type. However, outside of that range, B1, F-type stars, for example, are much different. It's not standard practice at the moment to correct for this, so we investigate this in our study. So we plotted the slopes of these spectral types here. So, yep, they span a large range. G2V is the sun-like star over there in red. And then we looked at the slope distributions for 1,300 asteroids observed by the Bus-Spinzel paper. They occupy distinct slope ranges and have narrow distributions. So we looked at the full width half maxima of each type, S, C, and X, and plotted it on the plot on the right. We can see that the G-type stars lie within the full width half maxima. However, the other stars lie outside, which mean that it could, but using those types of stars, it could change the overall classification of our near-Earth asteroid. So we applied that correction to the slopes, and then we used a principal component analysis following the Bus-Spinzel paper. It classifies the strength of the three main spectral features that we talked about earlier. This was a lot of work, so I'll spare you the tedious details, but this is the result. So the green dots are the results from the Bus-Spinzel paper, and the red dots are our results. Of the 20 unique near-Earth asteroids, some had multiple observations, so that's why we have 25. We have the results of 25 objects. We drew regions on the plot where C-type, X-type, and S-type lie, and classified that this way. And we also classified using qualitative description and the slopes we saw before. That reclassified two of the spectra from our principal component analysis. So as showed before, this is the thermal infrared surface composition plot. We matched our newly classified near-Earth asteroids to the albedo and diameter data, and we matched it to Neowise and Spitzer, and we overplotted. And you can see here our results. Lies in that range. So we found that S-types extend down by a factor of 10, and they lie in the albedo range for consistent with the larger type asteroids. For C-types, we only found one, and although it seems to lie in the albedo range for larger C-type asteroids, it suggests, however, that the selection effect may not, it may be due to a selection effect and not a physical difference. So we can use this extended plot as a tool. We can find albedo from the composition or the composition from the albedo. So we start with finding the composition from the albedo. So we started by separating out S-types and C-types into their albedo bands, and we found the mean albedo of each band. And then we determined the completeness and purity of each sample. So the purity is just the fraction of objects in the fraction of objects in this band, or the S-type band, for example, and the completeness tells us how many S-types are missing from that band. We tried different bandwidths, so we just changed it, and measured the purity and completeness at different steps. So these are the results. There's a trade-off between completeness and purity. So if you want more completeness, you have to have less purity, and vice versa. So we took the intersecting point as a good compromise. So we found near-Earth asteroids with about 0.23, in the 0.23 range, to be classified as S-type with 80% confidence, and C-type asteroids with in the 0.05 range with 70% confidence. Conversely, we can find the albedo from the optical spectra, and we do that by using the albedo distribution on the albedo surface composition relation plot. So we just took the mean values of the two distributions and found the full width half max, and that was found to be 0.23 and 0.05 for C-type. So what that means is that, using the conventional range, the volume is uncertain by a factor of 15. However, using this method, using the distributions, we've improved it up to a factor of 3.5. So, to conclude, we determined the composition of our 20 unique near-Earth asteroids. We found that although it's not standard practice to correct for the solar analogues, there is indeed quite a large correction that needs to be made specifically for solar analog stars outside of the G0 to G5 range. Outside of this range, it could potentially change the classification altogether. We managed to extend the albedo surface composition relation down by a factor of 10 for S-type asteroids, and the single C-type asteroid that we observed implies that perhaps it's not the turn-up at smaller diameters, maybe a selection effect. So we determined the composition from thermal infrared albedo at between 70 and 80% level, which gives approximately a 4 times better volume or mass than no data at all. So I'm currently working on a new project, figuring out how much Gaia is going to improve orbit determination for many near-Earth asteroids, many of which are now lost after discovery. Okay, thank you very much.
Thanks very much, Chris. Time for a question. Yes.
So, from your plots, it seems that there are some asteroids with very small error bars that are really, really white, that are like
You mean in this plot?
snowy,
No? Oh,
snowy in their albedo.
this plot, yeah.
That's, I didn't know that.
Which one are we talking about?
Well, so albedo is approaching 1.
Oh, yeah, so we don't, it seems strange that we also have C-type, which are potentially, well, they're dark asteroids, naturally, with albedos close to 1. We're thinking this might be some kind of selection effect, or we're not sure.
Don't know.
We don't know.
That's not our data. So
Yeah, this is,
The error bars are small.
yes,
yeah. So,
that's strange.
from NeoWise, Mainzer, Amy Mainzer.
Even comets don't have albedo now.
Yeah, we don't know what that is.
Could it be a mistake? No. Don't tell them, maybe I said.
Josh, you had a...
Actually, I just had a quick question on your very last comment about using Gaia.
Yeah, yeah.
The sampling from Gaia is what? Because these near-Earth asteroids you have to follow fairly frequently, right?
Okay.
If the Gaia, coming out with a new data release every year, I would think you've not got enough intervening points. Is that right?
That's not what we do. Explain what we do.
No, so
Because we're trying to track
No,
near-Earth asteroids.
we're not tracking any near-Earth asteroids in Gaia.
So we're trying to figure out whether, upon subsequent apparition, or whether we can determine the orbit well enough of the near-Earth asteroid so that upon subsequent apparition, we can figure out whether the asteroid appears in the field of view of a typical imager.
No, the key
No?
point is we're using the Gaia astrometric grid,
Oh, right.
which goes down to 20-something, 20 magnitude. So every image we take, say it's peaceful, will include a number of stars in 10 million seconds. So that's way better than we've had before. And we now, by taking isometric noise observations of the asteroids, also get to 10 million seconds, and then we have a much better defined track in the sky.
Okay, I think it's time to move on. Thanks very much, Chris. So next up, we have Alex Lascelles, who hails from, are you really from Southampton? You put Southampton in your vitae as well, but you're at Southampton University, so you're a local now. Yeah. Alex is a keen piano player. He plays past grade 8 piano, and he's a keen jazz pianist. And in addition to playing jazz, he's also taught jazz piano. He's a university first-team badminton player. Not a very common game in the US, but much bigger in the UK. So, university badminton player. Now he is changing gears a little bit, changing fields after doing some astronomy and physics. He's going to do a master's and then probably a PhD in neuroscience at Goldsmiths College in London. And it sort of occurred to me that he's actually going to work out why astronomers are so weird. Now he's actually heading as a celebration after this. He's doing everything completely right in this way. He's going to New Orleans tonight. He's actually taking a plane this evening, flying down for a little bit of relaxation this evening after this talk. So his his master's thesis has been with under the supervision of Cecilia Garafo here, and it's on the realistic MHD modeling of wind-driven processes in cataclysmic variable-like binaries.
Okay, thank you very much, Jeremy. As you say, I am working with Cecilia Garafo to study realistic MHD modeling of wind-driven processes in cataclysmic variable-like binaries. So cataclysmic variables, or CVs, are close binary systems normally consisting of an M dwarf or K dwarf type star, which accretes matter onto a white dwarf via an accretion disk. What I was doing is looking at MHD simulations, and I'm trying to investigate the mass and angular momentum loss rates for these type systems. So for CVs, their evolution is controlled by two main angular momentum loss processes, either side of the so-called period gap. And the CV period gap is an empirical lack of observations between orbital periods of 2 and 3 hours. We believe that below this gap, the angular momentum loss is dominated by gravitational radiation, and above the gap, it's associated with the magnetized wind of the secondary through a process that's called magnetic braking. So magnetic braking, this occurs when matter contained within the magnetized wind becomes decoupled from the secondary star. This creates a braking torque which removes angular momentum from the system. And this generally occurs at the Alphen surface, which is the collection of points where the wind material has sufficient velocity to decouple from the system. This happens at Mach numbers of 1. Using this, you can determine the mass loss rate and consequently the angular momentum loss rate. So why is it important to study this? Well, we understand the region below the period gap that's dominated by gravitational radiation. We understand that quite well, but we really don't know that much about what happens above the period gap. And so we want to better understand CV evolution through this. These systems are also known to be type 1a supernovae progenitors, so understanding them and their evolution is important. At the moment, observational measurements of stellar winds is very hard to do. Normally, you'll rely on stand-ins such as metal lines from when the stellar winds interact with the interstellar medium, and this can only give you an upper estimate in some cases. So we want to use simulations because we can look at a whole range of parameter cases, and we don't have to rely on these stand-ins. So the current assumption for magnetic braking is that for CV-like systems, it follows the same prescription as for a single star. However, this work by Cohen 12 has shown that when you include the white dwarf, you actually can reduce the mass loss and the angular momentum loss rates by up to an order of magnitude. So we're using the block adaptive tree solar wind row upwind scheme, or BATSRS. It's an MHD model that is used by the space weather modeling framework, which is what we currently use to look at solar winds. Is what we normally use. And how it works is you solve a set of MHD conservation equations for mass, energy, magnetic induction, and momentum. And the model self-consistently calculates the coronal heating and the wind acceleration, which is due to Alfvén wave turbulence dissipation. This is the currently accepted method that we believe drives the solar wind. We assume that we're treating a synchronously rotating diskless case, and we're ignoring centrifugal effects, and we assume it's spherical bodies, so there's no tidal stretching. So what we use is magnetograms, and these act as the initial condition for the magnetic field of the secondary. For this, we're using perfect dipoles. We then conduct a series of time-independent and time-dependent simulations using Hydra. Hydra is the Smithsonian high-performance cluster, and we use roughly 500 cores per simulation, and it can take up to a day for the time-independent and up to a week for the time-dependent simulations to run. So this is a table summarizing the sets of cases that we're looking at. So firstly, set A, we're just trying to have a standard case where we can compare to. Then we increase the white dwarf magnetic field strength to 50, and we also look at what happens when you increase the white dwarf mass. So before you can start analyzing the simulations, you have to have something to compare to, which in this case is just the single secondary star on its own. So this is a slice through the 3D solution in the y=0 plane. You can see the white circle in the center is the secondary star, and the white line is the Alfvén surface. And we've colored this plot by wind velocity. So you can see here that we see very slow winds in the equatorial plane, and these get accelerated up to 400 to 800 kilometers per second. And then we have quite high velocity winds for the polar regions. If we look at the same plot in density, you can see that the mass density traces the areas of slow winds quite well. So onto the results. And what we do is, for each set of cases, we look at both aligned and anti-aligned fields for the binaries. And we do this over a range of orbital separations. So here I'm showing it for 5 solar radii. And you can see that the anti-aligned case produces a more symmetric solution. And we see an area of slow winds behind the white dwarf. If we look at what happens when you increase the magnetic field strength, you get even more slow winds as the magnetic field lines interact. And then when you increase the white dwarf mass, you get an area of very high accretion just in front of the white dwarf. This shows up as high velocity winds. So now I'm going to show you one of the time-dependent solutions, which was carried out over the course of a week. And you can see here that as the solution progresses, winds are accelerated out. And you can see in this plot what looks like some lobes around the white dwarf, which we actually believe are the vectors for the wind velocity coming in and out of the plane. So we see a slight turbulent effect behind the white dwarf, and we believe this is due to a process called Kármán vortex street, which is, it would be the 3D manifestation of this. And it's the same effect that causes power lines to make a noise when wind passes over them, and it's what caused the Tacoma Bridge to collapse. So now If we look at the white dwarf wind accretion, this plot is just showing the secondary in the middle and the white dwarf where we've drawn a sphere around and we coloured it in by mass flow. And we've done this for the 10 Gauss case and the 50 Gauss case. And what we see is the higher magnetic fields create a more complex pattern of accretion, which is expected. And we believe the low field strength case has a more homogeneous pattern because it's more hydrodynamically dominated. So when we look at the plots for the wind accretion, we've got wind accretion rate on the y-axis and orbital radii on the x-axis, and we see that as the radius increases, accretion decreases, which you would expect. We've overplotted the Bondi-Hoyle accretion rate, and this is the rate of accretion which you would assume if there were no magnetic fields present. We see it represents the first case quite well, but it underrepresents on the second case. We did the same for the higher mass, and we see now that it actually overestimates the case. And we see over all of these that anti-aligned field configurations actually give the highest accretion rates. So now we look at the mass loss rates. So we integrate over the whole sphere, the whole domain, and we see how much mass is leaving the system. You can see that there is a trend of mass loss rate increasing as you go to higher orbital radii. We've drawn on the single secondary star at the top. So all of our simulations, when we include the white dwarf, we produce a reduction in the mass loss rate. Again, we see that anti-aligned field configurations produce a higher reduction, and we believe this is because these cases it's more easy to close field lines which can more easily accrete ionized material onto the white dwarf. So this is just some numbers for the three cases, and we see that the 50 Gauss case actually produces the most, and it can be up to 4 times a reduction when you compare it to the single secondary star. So finally, if we look at the angular momentum loss rates, we see a similar trend, but a bit of a higher scatter. We believe this scatter is because we're now integrating over the surface of the Alphen surface is what we're integrating over, and that's more variable with time than the whole domain. We see the same effects where anti-aligned field cases produce a higher reduction in angular momentum loss. So again, some numbers. What's important is we can get up to a 6 times reduction when you compare it to the single star. So to conclude, we've conducted 3D MHD simulations to look at what happens when you change the white dwarf mass and the separation, and also what happens when you increase the field strength and you look at different alignments. We found that accretion is most efficient for the anti-aligned cases, and we see this as the biggest reduction for both angular momentum loss and mass loss rates. And we can see up to a 4 times and a 6 times reduction when you compare to the single star. And all of these are dependent on the parameters which we simulate. And so we argue that this should be considered in future CV orbital evolution calculations so that we can try and understand what is happening above the CV period gap. Okay, thank you very much. And I'll take any questions.
Questions? Roseanne, yes.
Oh, that was fascinating. When you were looking at your closer orbital separations, was the donor star filling its Roche lobe?
So actually for these simulations, we're not including any Roche lobe overflow. So we assume the bodies are spherical and there's no tidal stretching.
But, well, I know you
But-
assumed that, but I was wondering about the the total mass transfer. It's a kind of an extension, I think, of what you've already done.
Yeah.
That if you have more mass per unit time on the white dwarf, then that, of course, will allow there to be feedback. And I don't think anyone has ever done this problem in this much detail. So I think it would be excellent. Now, I know you're going on to something totally different, and I'm sure you'll do equally excellent work in that. But I think maybe for future students, this is just an absolutely fascinating thing to have considered. And I think you're right, it does have implications for the future.
Josh and then. So, very nice. I was puzzled. Why are you considering wind accretion in cataclysmic variables? They're all essentially powered by Roche-Low overflow. So,
It's
something at the start.
It's because we're trying to look at the region above the period gap. And in this region, we believe the most of the angular momentum loss is because of this effect. Actually, I'm not sure if that's quite right, actually. Yeah. So I think we actually want to have a kind of simplified case. It's very hard computationally to include Roche-Low overflow. As you can see, it takes about a week to run a simulation. So I think that would be an avenue you could explore.
It's a theoretical experiment.
Yeah, so we wanted to see the difference that it makes when you include a white dwarf in the system. And even though you might not be able to observe this accretion as well as the overflow, if there is a change because of reconnection of the field lines, then we want to know that we're not overestimating the underlying development rates and mass loss rates and dynamics.
Yeah, it's also relevant for the measurement of mass loss rates on M dwarfs that are detached. The detached systems, you can actually use the wind accretion rate to understand what the real mass loss rate from the M dwarf is, which is essentially impossible to measure using standard techniques on single stars. Yeah. Anyway, Julian.
So, very nice talk, by the way. So, how scalable is your approach in the sense that you're predicting that when you have this white dwarf, you're getting lower mass loss rates and lower angular momentum loss rates than with the star alone? I'm asking, so this means that, for instance, if I consider a hot Jupiter case, a star with a hot Jupiter will have a smaller mass loss rate than a star alone. Can you apply the same, because your field strengths are comparable, for instance, to the field of Jupiter, right? So
Yeah. So I think it would be possible to apply that. We're only including the white dwarf as just an extra set of boundary conditions. So it'd be very easy just to change the mass or the field strength.
how important is the gravity of the white dwarf?
I think that is quite important. I haven't myself looked at that, but it would be definitely more important the closer you get, because we're starting from 3R, which you might be able to get even closer, but we were limited computationally. So
I think we did have two different masses that we explored for the white dwarf, right?
Yeah.
So I think mass makes
Yeah.
a difference. And so in the case of the lower magnetic field, we tried a lower magnetic field and a higher one of the
Yeah.
white dwarf. And the lower magnetic field showed that the alignment doesn't matter. So I think the lower magnetic field was not doing much, and it was mainly gravity. But then when you increase the magnetic field, you can see that the effect goes in opposite directions. And so that will translate in whatever mass you
Yep.
put to the hot Jupiter. The magnetic field itself seems to have an effect. So I think you can apply it. But I would like to mention that these 10 and 50 Gauss are on the white dwarf surface. These correspond to 10,000 Gauss or so, because we're using, just for computational reasons, we're cutting off at a bigger radius than a white dwarf would be, and reducing the magnetic field accordingly. So these are much stronger magnetic fields. So in that case, I think it depends on the separation of the hot Jupiter, but it might not be strong enough fields you have.
forgot to mention, but when you do buff the mass, you do see an even bigger reduction in mass loss. So,
Okay, thanks very much, Alex. Okay, well, somebody has to be last, and unfortunately, it turns out to be Anna, who wasn't very happy when she saw the running order. So Anna hails from Warwickshire in the West Midlands. She did undergraduate research project in galactic dynamics, among a couple of other things, in Southampton. She will be, after leaving here after the summer, she'll be starting a PhD working in protoplanetary disks in the group in Exeter University in the UK. She's essentially one of the top groups in the UK studying star formation and planet formation. But her work during this period of time has been with Joe Hoare and Kuju Zhang as advisors, and it's been on the topic of massive young stellar objects in the infrared dark cloud, G79.3 plus 0.3.
Very catchy name.
Exactly.
Yeah. Is this microphone working?
Yeah.
Okay, cool. Yeah, so I've been looking at massive stars in particular because they're very important on their surrounding areas. For example, when the massive stars are first forming, they can eject heavy elements into the interstellar medium, and that will affect all subsequent star formation in that region. They're also pretty mysterious. No one quite knows how exactly they form, and they're difficult to observe, which doesn't help trying to work out how they form. So this project has been looking at the massive young stellar objects in this particular infrared dark cloud, just as a way of testing perhaps some of the massive star formation theories. Does this clicker work? No, okay. So there are a YSO is the youngest stage of star formation after a molecular cloud has fragmented into stellar cores, but before those stellar objects have become hot enough to start fusion and move on to the main sequence. So there are 4 different types of YSO, and this is just a diagram showing what's going on there. So as you move from class 0 at the top of the screen to class 3 at the bottom, that's the object evolving in time. The left panel is showing the spectral energy distribution of the different classifications, and the right panel is showing the structures of the objects. So the class 0 objects are just the central core that's spherically accreting all the surrounding material, whereas by the time it's class 1 and above, this material is instead accreting onto a circumstellar disk. And the different structures of the objects with different classifications mean that the SED is a totally different shape for each classification. The very youngest class 0 and 1 objects as well show outflows of material from the objects, which will be important later. So the SED shapes are useful because it's very difficult to observe YSOs, and you cannot resolve the central objects itself from the disk just by looking. What you can do is measure photometry across a range of wavelengths in the infrared and millimeter, build the SED, and then from the shape of that SED you can deduce something about the structure of the object that you can't tell just from looking. So we've been using data from Spitzer and the SMA in particular to look at these objects. YSOs form in various places, including infrared dark clouds, which is what we've been focusing on. This is our cloud, called G79.3 plus 0.3. That panel on the left is showing the central section of Cygnus X. So our cloud is right in the center of Cygnus X. And this inset on the right here is showing just our cloud region. This is a composite image from the Spitzer Space Telescope. So this is an entirely infrared image. So Cygnus X is one of the nearest massive star-forming regions to us. It's 1.4 kiloparsecs away. And there's plenty of evidence that there's lots of massive star formation happening in this complex, such as the presence of infrared dark clouds, as well as OB associations with hundreds of massive stars and H2 regions throughout the complex. So in this image in particular, you can see some of those bright point sources are some of the YSOs we've been looking at, and the infrared dark cloud you can see is that darker region in the background. I think you just about see it sort of stretching towards the left and towards the top there. And that's because infrared dark clouds are opaque in the infrared. And because we want to be searching for the very youngest objects, then we want to look at this region in longer wavelengths to see right to the center and see the least evolved objects. So we observed the cloud using the SMA at 1.3 millimeters. The SMA is an interferometer on Mauna Kea in Hawaii. It can observe using millimeter wavelengths at very high and get very high resolution images. So this figure is showing that same cloud region. That's just the colours are showing the emission strength. So darker colours mean stronger emission. And we see 5 distinct YSOs in this region. 3 of them we've seen before with infrared instruments such as Spitzer. So we'll be able to do this to build their SEDs, but I'll get to that in a bit. We can measure the flux of these objects individually, and we find that they're between 39 and 150 millijansky. And that gives us an indication of the mass of the material surrounding these objects, the dust and gas surrounding them. This is directly proportional to the flux of the objects, and we see that there's at least 1 solar mass of material surrounding each, which means that there is some potential for these objects to continue accreting that material and growing in size. Objects 2 and 3 show extended emission. So rather than appearing just as black circles, I think you can just about see on that image, there's some fainter grey emission right next to them. So on object 3, that's going from the centre of the object up to the upper right corner of the image. And that extended emission is a sign that there are outflows of material coming from those objects. So to find out more about those outflows, we use the spectral capabilities of the SMA. And here are some examples of the spectra that we saw. So these spectra are for the region that contains the SMA objects 1, 2, and 3 and some of the cloud area around it, rather than belonging to any one particular object. And at certain frequencies, there's very strong emission. And that's to do with the de-excitation of electrons as they move from higher energy states to lower energy states. We've been focusing on the carbon monoxide emission because it's the strongest by far line emission that we've seen. And with 12CO, we can trace any outflows from these objects across the regions because 12CO, that's what it does. I was about to repeat myself. Yeah, so this is the result of mapping that 12CO emission, and we use this to show the velocity of the outflow across the region. So in this image, the green contours are the continuum emission from before, so that's SMA objects 1, 2, and 3 again. The extent of this image is the entire region covered by the SMA. And the blue and red contours are showing the blue shifted and red shifted emission, velocities from the outflow. So that's covering plus or minus 10 to 50 kilometers per second in steps of 6 kilometers per second. We find that this outflow is really long. It covers our entire region, so it's at least 1.4 parsec long. And it's unusually massive compared to other nearby outflows. We've also found parameters including its momentum, energy, etc. So going back to photometry and spectral energy distributions, here are the SEDs of our SMA objects that have been previously observed. So this is using photometry from 2 Massey Good, Spitzer, Herschel, and now with the SMA. So in these images, the round markers are data points, are the flux measurements. Any triangular markers are upper limits in flux. And the line is a YSO model fit. These models come from the SED fitter by Thomas Robitaille, and it's just a grid of 10 million possible YSO spectral energy distribution models that cover the entire parameter space. And there's software to find the model that best fits our data. So we can take the model, the parameters, that the mass, luminosities, etc. that we use to create that model, and use them as a first estimate for the parameters of our objects. So using this, we find that the SMA objects 1 and 4 in particular are unusually luminous, and they have very high masses. So they're already above 6 solar masses, and they're still, because they're class 1 objects, they're still actively accreting. So they're only going to become more massive in time. So we can say with pretty confidently those 2 objects are going to become massive stars. I also did this SED fitting process for every single YSO in the entire Cygnus X region. There's 30,902 of them, and they are mostly class 2 objects, so that in the same way fitting these SEDs, it gives the parameters. So I'm just comparing the mass distribution here. The top panel is just showing the class 2 objects in Cygnus X as a whole. The middle panel is just classes 0 and 1, and the bottom panel is just the 28 objects that are covered by our SMA data. So the top panel, I've just split those 2 apart because there's 10 times as many class 2 objects in Cygnus X as anything else. And so that top panel is essentially showing the distribution of the whole region as well, regardless of class. So if we look at the bottom panel and the class 1 objects, we see that the distribution tends to be skewed towards higher masses than for the panel just above, as Cygnus X as a whole. So, and if we use the bottom panel as an indication of the initial mass function of the IRDC, just as a very rough estimate, that would indicate that the stars in this region are on the more massive side. In addition, our SMA objects 1 and 4, those vertical lines are just showing the positions of the our SMA objects. SMA objects 1 and 4 are the 2 most massive in the IRDC and in the top 1% most massive across the whole region. Just quickly, I've done the same thing with extinction, so the layout's the same as before. We see that the class 0 and 1 objects tend to have much higher extinctions, and comparing the bottom panel, just our IRDC, with the top panel, we see that the extinctions tend to be higher, and that's as expected because we're looking right in the center of this IRDC for the least evolved objects. So we would expect them to be high extinction because they're going to be surrounded by a lot more material. One last thing here as well is that in Cygnus X as a whole, I said it's 90% class 2 objects, whereas in G79.3 it's exactly half and half between class 1 and class 2 objects. So again, we've got an unusually high number of the less evolved objects, as would be expected in the younger region. Okay, so in conclusion, we've used the SMA to resolve 5 YSOs in G79.3 plus 0.3, one of which has an unusually massive outflow. Two of these objects are the most massive in the whole region, and generally we find that these objects are on the more massive high extinction side, and that there's more class 1 objects in our RDC. And all of that is consistent with this cloud being the birthplace of massive stars. Thank you.
Thank you very much, Anna. Any questions for Anna? Yes, one at the back.
Is there any significant degeneracy between young objects and an older object that you're seeing with just more edge on, so you're looking for more discs, so its SED is more infrared? Is there like a lot of that going on? Or?
That is a thing that happens, but I don't know how much I have to account for it, I'm afraid.
Yes, Roseanne.
Your objects that were relatively close together, now I know this was a big region, it was something like 22 parsecs, is that?
That subsection was only about 1.5 parsec.
Well, that's why I was asking, because that particular part of it looked small enough that perhaps you might be looking at regions where the stars could be bound to each other, or could become bound. Is that, so this is really not what you did. I was fascinated by what you did and by finding these masses and outflows. I'm also interested in binary, so I was just wondering, is there any possibility that those stars might become bound, or that there might be smaller stars hidden there? Would you be sensitive to very low mass objects that could be bound to one of these objects?
I'm not sure about that last bit, but certainly those 3 objects are, I wouldn't be surprised if they're interacting in some way.
It's very interesting. I found it fascinating that you're able to map out the masses and study the distribution. It'd be quite interesting to study spatial correlations as well.
I do actually have that. I've got an extra slide somewhere, but I've got like 30 extra slides, so give me a moment.
You were very prepared.
Yeah. Also, this is not working. There we go. Yeah, there we go. So, where I had those 30,000 objects before, this isn't all 30,000, this is just the ones that are immediately surrounding our area. And generally we were finding that the most massive objects are in the infrared dark clouds. So that blue, terribly drawn outline is my cloud. And you can also see this other dark region. Oh, thank you. How do I? Yeah, just there as well. There's also an unusually high number of the class 1 and the higher mass objects there.
That's very interesting. Thank you.
Okay, any last questions for, yes.
So your outflow is remarkably well aligned and remarkably long, and it strikes me that this might be a contribution to what has been something of a puzzle, which is that the CO outflows that are normally observed are not nearly so well collimated, whereas optically you see terms of arrow objects, and they look really weird and very long. And this looks like a CO outflow that's something like a Herbert arrow object. So I'm just saying it's sort of interesting in that respect.
Yeah, I didn't really go into it, but I was looking at another region and things like, well, I was reading someone else's results on it, the DR21 region, which has a lot of objects with outflows in a very small space. And the difference there is that the objects themselves are much more massive, but the outflows much less massive than these ones somehow. And they're interacting a lot as well, I believe. It's been a while since I've looked at the image, but even within Cygnus X, this is perhaps a weird case.
Okay, I think it's probably time to wrap up, but thank you very much, Anna, and thanks for all of you.